So this is the clip for the second part of today's lesson, and that's section 3.4. That is called Moivre's theorem. Moivre's theorem. Moivre's theorem. And in this section, there is the proof that you definitely need to know, because it happened twice already that it was as part of the released exams. I mean, it really happened, the proof really happened on the exam. Okay, so you definitely need to know how to prove it. I'm not going to do it here. I will tell you where to find it. You study it. Of course, if you will have a trouble understanding or so, then you can always ask me. But once I'm back, I will check if you did learn it and if you do understand it, okay? So definitely go over. I will remind you on the OneNote as well. So the proof itself, proof is on page 28 and page 29, because there are two cases: n is greater or equals to 1, or n is negative integer, okay? So study that later. Negative integer, I will remind you on the OneNote. So what we just going to use it now. So Moivre's theorem says basically this is the statement here, this one. Okay, so what is happening is that when you have the z as a complex number, you can have it written obviously in three forms. You can have it as x plus yi, or you can have it written as r times cosine theta plus I sine theta, or you can have it also in the exponential form, and that is r times e to power of I theta. Okay, but then it says that z to power of n is equals r to power of n times cosine n theta plus I sine n theta, or if it's written in the exponential form, then of course it's r to power of n, and then you would have e to power of I n theta. That's the same story. Okay, so we're going to use it straight away, but again, the proof can be found on page 28 and page 29, and you do need to know it. You do need to be able to prove it on your own. The proof is by induction. That's what you learn in FP1. Okay, so there should not be any trouble. Okay, so question 1, let me see this one. So what we're going to do here, again, look at the argument. Argument here is pi over 6, and modulus is 1 in both cases. What is good? Because that means 1 to power of 5 times cosine and the multiple of the argument, pi over 6 plus I sine 5 pi over 6. Okay, so you basically take the exponent and multiply the argument with it. Okay, and of course modulus must be raised to the same power as well. So the same story is in the E case. It's 1 to power of 5. What is 5? Oh, sorry, what is 1? What the hell? Cosine, and it would be 5 times 2 pi over 5 plus I sine 5 times 2 pi over 5. But what you can notice, again, in the first case and second case, I can also simplify it, because 5 cancel out, 5 cancel out. So then this one can be written as cosine 2 pi is 1, and sine 2 pi is 0, so plus 0i, okay, or actually just 1. In the first case, we didn't do it, but we can. 5 pi over 6, so cosine 5 pi over 6 is negative root of 3 over 2 plus sine 5 pi over 6 is 1/2, so 1/2 I, because this is obviously 1. Okay, so this is very easy actually. There is nothing special about it. You just learn the rule and you apply it, but again be careful because you need to be able to prove it as well. Okay, so moving on. If there is now this is combination of the section 3.3 and 3.4. So before I can simplify it, so I'm going to try to squeeze it here. So this would be this would be cosine 5 theta plus I sine 5 theta over cosine 4 theta plus I sine 4 theta. And now because there is a plus and plus in both cases, I can just apply the rule from section 3.3 about the division of complex numbers. That means in this case it would be cosine theta plus I sine theta. The reason why, because this is 5 theta minus 4 theta obviously, and this is the same, 5 theta minus 4 theta. For the I case, that's a little bit more interesting, because what you can see there, let me see. I case, I think I will not have enough space, so I'll write here. I case. So when you look at it, you have 1 divided by something, but obviously that 1 can be written as 1 times cosine 0 plus I sine 0, okay, or 0 theta if you want, 0 theta. And then you have cosine 2 theta plus I sine 2 theta to power of 3. So first rewrite that, cosine 0 theta plus I sine 0 theta over, now I'm applying the Moivre theorem, so it's cosine 6 theta plus I sine 6 theta, and now I'm applying the rule about the division of complex numbers, so it would be cosine minus 6 theta plus I sine minus 6 theta, but this can be simplified because cosine of negative is the same as cosine of positive because of the even function, and minus I sine 6 theta. And now the k case, be careful here because there is a minus. So before simplifying, we need to modify that. Cosine 5 theta plus I sine 5 theta over cosine minus 3 theta plus I sine minus 3 theta, and this would be to power of 2. And now because I have plus and plus, then I can apply the rule from the Moivre theorem first. 5 theta plus I sine 5 theta, there was nothing to be modified, and in here I have cosine minus 6 theta plus I sine minus 6 theta, because I multiply by the exponent, this goes down, you multiply it, so it will happen to be cosine, again because I have modulus is 1 in both cases, right? Otherwise it would have to be 1 divided by 1, but that's equals to 1. So 5 theta minus 6 theta plus I sine the same story, 5 theta minus 6 theta. So I have cosine 11 theta plus I sine 11 theta. Wait, let me see. Have 5 theta minus 6 theta. Yes, that should be fine. 11 theta. Good. I think I prepared one more. Let me see. Evaluate. That's this one. Okay, easy, but again we need to modify in the middle, the minus in the middle. So the first one I can directly multiply it, so it would be 4 times 7 is 28 pi over 13 plus I sine 28 pi over 13 over this one. I'm going to modify first, but I'll write it here, okay? So cosine minus 4 pi over 13 plus I sine minus 4 pi over 13. And this is to power of 6. That means it would be cosine negative 24 pi over 13 plus I sine negative 24 pi over 13. Now when I divide it, then I need to subtract the arguments. So 28 pi over 13 minus 24 pi over 13 plus I sine, the same story. I said 28 pi over 13 minus 24 pi over 13. And this would give me 52, and 52 divided by 13 is 4. So cosine 4 pi plus I sine 4 pi. And cosine 4 pi is the same as cosine 0, so that's 1. And sine 4 pi is the same as 0, so sine of 0 is also, so 1 should be the answer. And then the last one. That's this one, I guess. Yep. So in this case, we have several options, but in these sections we will discuss the options where you can rewrite it using the modulus argument form. Like for example, a case. So when you look at the a case, it's 1 and 1i. That's this. So this would be 45 degrees, obviously, yeah, or pi over 4. And argument is pi over 4, and the modulus is root of 2. Okay, so this number, 1 plus I, can be written as root of 2 times cosine pi over 4 plus I sine pi over 4. Okay, now if I have 1 plus I to power of 5, that means this, all of this, will be to power of 5. And there I can use the Moivre theorem. So root of 2 to power of 5 times cosine 5 pi over 4 plus I sine 5 pi over 4, because I multiplied by the exponent 5 and 5. Okay, and then you can simplify it, because root of 2 to power of 5 is 2, so 4 root of 2 times cosine 5 pi over 4. That is in the third quadrant, so it's negative root of 2 over 2 and negative root of 2 over 2i. And so when you simplify this, let me see, so 2 cancel out, so minus 4i. Right, so that's it. And I'll do the b case as well. So minus 2 plus 2i to power of 8. And similar story. First we need to see minus 2, 2i, so that's this. I need to know the argument, and I need to know the modulus. The modulus in this case would be 2 squared plus 2 squared, what is root of 8 to root of 2. And this is 45 degrees, so argument would be 3 pi over 4. Okay, so this is the same as 2 root of 2 cosine 3 pi over 4 plus I sine 3 pi over 4 and everything to power of 8. Based on the Moivre theorem, it says this is to the power of 8 times cosine 24, or okay, I'll write it this way. 8 times 3 pi over 4 plus I sine 8 times 3 pi over 4. What is 6 pi? So this would be 2 to the power of 8 times 2 to the power of 4 times cosine 6 pi plus I sine 6 pi. This would be 0, obviously. This would be 1, obviously. So this would be together 2 to the power of 12. 2 to the power of 12. 1024, 2090, 2048. So 4096. 4096. Good. So now once again go to OneNote and check which exercise you should try. You can find the solutions in the